All right, this is where it's going to get difficult. So let's talk about genetic recombination. Oh man, this is going to be some good stuff. So Thomas Hunt Morgan, we talked a little bit about maybe in some classes. I think I took this out of the PowerPoint later on, just because I wanted to focus it more on this section. But he worked with fruit flies, and he analyzed their gene frequencies from parent to offspring. And interestingly enough, he didn't accept Mendel's inheritance pattern, and he went out to disprove it. So what he actually did was he was looking at fruit fly phenotypes, and we can see here we have red eyes, we have purple eyes, we have normal wings, we have vestigial wings, and you can see these genotypes that are going to code for each. Now you can see when these are crossed, the same thing happens with Mendel's plants, where these kind of recessive traits are going to be masked. Now, what happens when you cross two of these guys in the F1 generation, you can see here, we're going to get the cross here. And they're going to get let me go back. Where are we at here? Yeah, so anyway, sorry. We're going to cross one of these fruit flies here with, again, the recessive, not themselves. I'm sorry, not themselves. So what's going to happen here, interestingly enough, if you look at the chromosomes and the crossing over, you should get 25%, 25%, 25%, 25%. So that means like a female with red eyes and she has the long wings. You have a another here with the purple eyes and the short wings, red eyes, short wings, purple eyes, long wings. So you can see here again, you're only getting one thing from here, but due to crossing over, you can get this chromosome, or the recombinant chromosomes. So that's what the data should look like, right? That's what Mendel should look like. Now he didn't know about crossing over, but he said, okay, well we're getting something here. There must be some genetic exchange, and then you can kind of predict that's not what happened, right? So what actually happened was you can see here he got a lot different numbers, and it's like, whoa, why are these different numbers? And the percentage here, yeah, it's not 25, 25, 25, 25. So what's going on here? It's like, and you can do this experiment time and time again. You get very similar numbers. You're not going to get those 25, 25, 25. So he couldn't figure it out. He said something's going wrong here, and he was actually teaching a genetics class, and he kind of proposed it to his students and said, "Hey, I don't know what's going on here. Can you think of something?" And kind of proposed it to them. So Alfred Strudevant, he was a student of Morgan's, and one night he blew off his homework and wanted to figure this out. So he figured out crossing over and actually figured out the process, and that genes are located on your chromosomes in different orders. I know it's like, "Oh my gosh, this is crazy, Mr. Friedhoff. Like, I can't believe it. Like, you're telling me genes are on chromosomes in different areas." Like, yeah, I know that, but like again, early 1900s, they didn't know any of this. It was like mind blowing. So we know that these chromosomes have these genes on them. Now, crossing over can occur between any two of these genes, but I like to start out here is where is crossing over going to occur most likely between A and B or B and C? And if you're thinking B and C, you're right. There's just more area for it to cross over. Between A and B, it's very unlikely for them to cross over and switch. It's more likely that B and C cross over. So you can see here, it's more likely that there's a crossing over event here than between these two. Yeah. So again, this is going to show us that not all Punnett squares are kind of created evenly, and it's really tough. This doesn't disprove Punnett squares at all. It just says that we have to think about genetic recombinations within a chromosome to be different. When they are on different chromosomes, Punnett squares work perfectly, but when they're not, yeah, not so much. So an analogy is like between gene 1 and 2, 3, 4, like you can do Punnett squares easily. But looking at the linkage between gene 2, 3, and 4, it's a little bit different. Gene linkage says that gene 2, 3, and 4 are going to be inherited more often than gene 1 and 2 because they're on the same chromosome. The crossing over between gene 2 and 3 is less likely than the recombination between 1 and 2. So let me go back here. This is a great way to say, again, if we look at the genes on this chromosome, you're more likely to inherit A and B than A and H together because they're so far apart. So the more close the two genes are on a chromosome, the more likely they're going to be inherited together. The further apart they are, the more likely they're going to be recombined. I'm going to go back to this image. We talk about people with red hair, red features. they inherit things like freckles, their red hair, and paler skin because those genes are very close together on the chromosome. It's less likely they only get one of them because they're so closely located on the one chromosome. So we're going to talk about genetic mapping and what this allowed Thomas Hunt Morgan and his geneticist buddies to do is to actually map out the chromosomes. I know you're probably thinking like, how could they map out chromosomes? They couldn't even really identify certain features of the chromosome, but yeah, they could use a little bit of math and map out the chromosomes. Each chromosome is about 50 map units long. If a gene linkage is more than 50%, genes are on different chromosomes. So that's easy for us to understand. 1% recombination frequency equals 1%. It's called a center Morgan after Thomas Hunt Morgan, but it's map units. I know I'm talking in another language, but let's do a couple practice problems. All right, so with drawing these chromosomes, what we're doing is we're actually looking for certain genes. We're trying to map them out in the chromosome. This is exactly what they did back in the early 1900s. Now, the great thing for us today is we don't have to do this. Oh, and you're probably thinking like, why do I have to do this then? It's a good practice and kind of logical thinking. I will only be interested if you can do the the 3 or the 4 gene chromosomes or the 4 genes on a chromosome, and they're pretty easy once you get the hang of it. So this is just kind of having you understand that the chromosomes that are further away have a more chance of being recombined than the ones that are closer. So it says draw your chromosome. Start with the largest percentage. So here we have B and C. So I'm gonna put B and C like here and here. And then it says you're going to place the other genes accordingly. So you can see B and C are all the way like here and here. Obviously, A and C and A and B are 12 and 6. If you add those up, they equal 18. So A has to be between B and C. And it looks something like, you can see this, like this. You can see how the A is a little closer to the C here in this case because it's between the A and the C, it's 6 and between the A and the B, it's 12. Now, it's not perfect. You can see it doesn't like 12 isn't double of 6. But again, this is just rough estimates of where these genes are on the chromosome. Our next one here is very similar. Again, there's only 3 genes. Again, remember we start out with A and B. It's the largest. We go here and here. And then you can see between A and C and B and C correspondingly is A and C is 8% and B and C is 9%. So this is a crossover frequency, which means how much is this being crossed over? So remember we put A and, let's see if you can see this here, A and B very far apart. So that's 17 between A and B. And then obviously 8 and 9 make up the in between. So you can see between A and C, there's 8. And between C and B, there's 9. Now, this stuff is pretty easy once you get the hang of it. With the 3 genes per chromosome, we're going to add in a 4th. And it's like, oh my gosh, there's a lot more math. All right, here's the one where there's 4 genes. You can see A, B, C, and D. And this is going to be a little bit more complicated, but again, it's not too bad. And this is as far as I really want you to go. You can do 5 or 6 genes, and it just becomes like Sudoku, which you have to like find where things go. But don't worry about those. I just want you to know these because I did see this on a previous exam from years ago. So this is not out of the realm of possibility for the AP exam. But remember, you start with your longest genes, and that's B and C. Now, if you look here between B and D, it's 40, so that's 40 map units. Now, if you go 40 the other way, you're not gonna be on the chromosome because remember, this thing is 50% or 50. I think they're called centromorgans long. So B and D also have to be. I'm sorry, C and D also have to be really close because again, remember, C and B are 45 away. That means D and C are only 5 away. And then between A and B is 15. So A is probably around here, and A and D is 25. That makes sense because if we add these up between B and A and D, it's equals 40, which is the B and D here. It's going to look something like this. So you can see here BADC. Somebody's going to say, hey, Mr. Fradoff, can you reverse order here and go CDAB? Yep, it doesn't matter because, again, if you're looking at it this way, I'm looking through it like kind of like a mirror. It can be either way.